Okay, so let's start. In the last class, we were talking about some concepts in algebra, particularly divisibility and basically division of polynomials. How do we divide polynomials? What irreducible polynomials are? Sort of trying to generalize the notion of prime numbers, GCD, and divisors from the integers to the set of all polynomials, right? So in particular, we saw that the way you define GCD is kind of important because the GCD may not be unique. One way of getting around that is to insist that the leading term in the coefficient, that is the coefficient of the highest degree term, is basically equal to 1. That's one way of making sure GCD is always unique. Then we saw how to divide two polynomials and how to find the GCD of any given any two polynomials. And then we defined an irreducible polynomial as one which is divisible only by itself and 1, or constants, scalars. So not all polynomials are irreducible, just like not all numbers are prime. But the idea was that it's possible to find irreducible polynomials, and we'll use these irreducible polynomials to construct finite fields. So from a prime field, we want to extend the notion of a prime field to higher order fields in some sense. So let's see the following. Right. So we stopped in the last class with the following statement that for any two integers a and b, you can always find integers c and d such that ac plus bd is equal to the gcd of a comma b. So in particular, if a and b are coprime or gcd is equal to 1, then ac plus it's possible to find integers c and d such that ac plus bd is equal to 1. And it turns out that this is an if and only if condition. So the GCD of A and B is equal to 1 if and only if AC plus there exist integers C and D such that AC plus BD is equal to, right? So let's see a proof of this. So in fact, I'll do it for polynomials, and therefore you can generalize it to the integers or any ring for that matter. Okay, so we want to show the following. So take any two polynomials, a of x and b of x. The GCD a of x, b of x is equal to 1 if and only if you can find polynomial c of x and b of x such that a of x, b of x plus b of x equals 1. So first, let's try to look at this expression a of x, c of x plus b of x, d of x. So suppose that this is equal to 1. Okay, what can we say about the GCD of A and B? Right? Now, if the GCD of A and B were not equal to 1, would something be violated? So suppose this is true and the GCD of A of x, B of x is something else, alpha of x, some other polynomial. Okay. My claim is that alpha of x has to be equal to 1. Correct? So how do you use it? So you know that alpha of x is the GCD of A of x and B of x. What does it mean? What does it imply? Correct. So alpha of x divides A of x and alpha of x divides B of x. So alpha of x divides A of x, C of x. Correct. And alpha of x should also divide B of x, D of x. So it must divide A of x, C of x plus B of x, D of x. So alpha of x must divide 1. When can that happen? When alpha is a scalar. So in particular, if it's the GCD, it has to be equal to 1. Okay. So since alpha of x is the GCD of A of x and B of x, we know that alpha of x divides A of x and alpha of x divides B of x. Correct? So alpha of x must divide A of x, C of x and B of x, D of x, and therefore A of x, C of x plus B of x, D of x. Right? But you know that this is equal to 1. Correct? So alpha of x should divide 1. Right? Which means that alpha of x has an inverse. And the only elements in the polynomial field are those for which are basically the scalars. So any other polynomial does not have, any polynomial of degree greater than or equal to 1 does not have an inverse. It's a field element, and since it's the GCD, alpha of x equal. Right, so this means that the GCD is equal to 1. So if there exists C of x, D of x such that A of x times C of x plus B of x times D of x equal to 1, then it implies that the GCD is equal to 1. So that's one part proved. Now what we want to show is that if the GCD is equal to 1, then it is possible to find a C of x and D of x such that this equation is true. Okay? Yeah. Yeah. Well, yeah. Okay. So this is, in general, this could be a, so just this statement itself implies that this is a scalar. It's a field element. It need not be equal to 1. Right? Because every field element has an inverse. And therefore it is possible to find some other elements such that alpha times theta is equal to 1. But now if we insist that the GCD always has the leading coefficient being equal to 1, then alpha must be equal to 1. because it's a GCD. All good? Yeah. But in what field? So this is not true in the integers, right? So if you sort of go through this proof, okay, so let's suppose that suppose that we're looking at the set of integers. Okay, I won't redo the entire proof, but suppose that instead of a of x, b of x, c of x, d of x, I have integers a, b, c, d. Okay, so I know that the GCD is equal to alpha. Therefore, alpha divides a and alpha divides b. So alpha divides AC plus BD. Alpha divides 1. The only integer which divides 1 is 1. Correct? But now if you're looking at the polynomial ring, then remember that if you look at F3, say F3, 2 divides 1. Correct? So that's the only statement that I'm making over here. It's some scalar. It could be 1 or 2 or 3. Sorry, not 3. It could be 1 or 2 in this case. Okay. So now so suppose that the GCD of a of x and b of x equals 1. We are given. What we want to show is that a of x, there exists some polynomials c and d such that ac plus bd is equal to 1. Right? So let us look at the set. So let us define the following set, which is the set of all a of x, b of x plus c of x, d of x for all possible polynomials c of x and d of x. Okay. I want to know what kind of a structure this forms. Right? So this set, the set of all possible a of x, c of x plus b of x, d of x, has some nice properties. So firstly, if I multiply this with any polynomial, I still lie within G. Right? Take any f of x in G. So f of x can be written as a of x, c of x plus b of x, d of x for some c and d. Okay? A and b are fixed. This G is defined in terms of a and b. Okay. So if I take any other, let's say alpha of x times f of x for any polynomial alpha, this still lies in G, right? Because alpha times f is alpha AC plus alpha BD, which is some a times c prime plus b times d. So this is also in G for all polynomials. Okay, that's one property. What else can we say about G? Does G form a group? So we know the set of all polynomials forms a ring, and this is potentially some subset of the polynomials. So there are only two properties that we need to verify: whether it is closed under addition and whether inverses, additive inverses exist. Is it closed under addition? It is, right? So AC1 plus BD1 plus AC2 plus BD2 is equal to some AC3 plus B. So the same form. And do inverses exist? Obviously, since C of x and D of x can be any polynomials, minus C of x and minus D of x also exist. So additive inverses also exist. So G is a group. What we want to now know is whether G is a proper subgroup of f of x, or is it equal to f of x itself? Potentially that could happen. It could be equal to f of x. Is it possible to generate all polynomials using? That is what we want to know. Suppose that it is a proper subgroup. What does it imply? It implies that no scalar. So suppose that one is in G. Right? If one is in G, if the multiplicative identity is in G, then what can we say about G? Yeah, no, G is a ring, I agree, but in terms of f of x, can I say that G is equal to f of x? Remember, we have this property. So if 1 is in G, then 1 times any polynomial is in G, which means that all polynomials are in G. Therefore, G must be equal to f of x. This is equal to the ring of all polynomials. But potentially, one may not be in G. So let us say that beta of x is the polynomial of lowest degree in G. Yeah. So, yeah, correct. This is implied by this statement. So G is a subset of f of x, right? Because how are you generating G? You're just generating it by adding and multiplying polynomials. Addition and multiplication of polynomials only gives you some other polynomial. So you can't get anything new, right? But potentially it could be a strict subset. That's all that we have, right? Okay. Now suppose that beta of x is the polynomial with the smallest degree in G. No, beta of x could be scalar 1, or it could be some other higher degree polynomial. We don't know at the moment. Now what I claim is that beta of x will divide both a of x and b of x. That's what I want to show. Okay, so if I show that if beta of x divides both a of x and b of x, then beta of x is equal to a c plus bd for some c and d. So so therefore, if let's get to that in maybe. Okay. So we know that beta of x is the polynomial of lowest degree, right? Since beta is in G, there exists some c of x and d of x such that beta of x is equal to x b of x d of x. Nothing new. Beta is in G, therefore I can write it in this particular form. Right? Okay. Now beta is the special element which has a least degree. So let me use the Euclid's division algorithm. So clearly a of x and b of x both lie in G, because I can write a of x as a of x times 1 plus b of x times 0. Similarly, b of x can be written in a similar fashion. So now I can write a of x as beta of x times some quotient plus a remainder. Correct? So let me call this qa of x and ra of x. Alright? I can write any given any two polynomials, I can always write it in this particular form. Okay? Where the degree of ra of x is strictly less than the degree of beta of x. Correct? Okay. Let me rearrange this particular thing. R a of x is equal to a of x minus beta of x to a of x. Okay, fine. All right, but what do I know? So a of x is in G, correct? Beta of x is in G. So beta of x times qa of x is also in G. So this term is in G, and G is a group. So this whole term is also in G. Right? So Ra of x is also in G. The remainder should be in G. But how can that happen? Because we assume that beta of x was the polynomial of the least degree in G. Correct? So this can happen only if Ra of x is equal to 0. Nothing else can give you this. This implies Ra of x is equal to 0. So this implies that we can write a of x as beta of x times qa of x, or basically that beta of x divides a of x. Yeah. Correct. So okay, so beta of x is the polynomial of the lowest degree, correct? And we know that Ra of x is also in G, correct? So Ra of x, the degree of Ra of x is strictly less than degree of beta of x, correct? So but then we assume that beta of x has the least degree, so that's a contradiction. This can happen only if Ra of x is equal to 0, because we know that 0 is in G, it's a group, right? And the only non-zero polynomial of the least degree is beta of x, correct? So Ra of x must be equal to 0. Since beta is the non-zero polynomial, least degree. Non-zero, yeah, exactly. So the zero polynomial is of course there in G, but this is the non-zero polynomial of the smallest degree. But then I can repeat the same exercise for b of x. I can write b of x as beta of x cube b of x plus rb of x. Once again, this implies that rb of x is equal to 0. and that implies that beta of x divides b of x. Correct? So beta of x divides a of x and beta of x divides b of x. But what do we know about a of x and b of x? The GCD is equal to 1. So that must mean that beta of x is equal to 1. But we know that beta of x is in G. So beta of x, so 1 equal to a of x, c of x, d of x. Any questions? No, we have proved that 1 is in G. We have only used the fact that the GCD is equal to 1. Correct. I have not used it anywhere. It's just a statement that I was trying. So I have proved that 1 is in G of x. As a consequence, G is equal to f of x. That's just a property. I have not used it particularly anywhere over here. Exactly. So now let's make one more definition. So just like we did modular arithmetic over the integers, we can also do modular arithmetic over polynomials. Right? It makes perfect sense. So we say that a of x is congruent to b of x mod f of x if the remainder when divided by f of x for both a and b are the same. The remainder a of x x, this is equal to the remainder b of x when divided by f of x. Okay, so sometimes we also write a of x mod f of x. This is going to be the remainder a of x when divided by f of x. Just notation. So what are some properties of the mod function? So if I take a of x plus b of x mod f of x, then what is this equal to? Sorry? Again, that's not enough. Sometimes it's a of x mod f of x plus b of x mod f of x, the whole thing mod f of x. in general, because a of x mod f of x plus b of x mod x. Okay, if for example, if you take integers, this could be greater than f. So if you look at, say, three integers a, b, and f, right? A mod f plus, yeah, the remainders could add up to some. But in fact, for polynomials, that won't happen. Because the degrees of both a of x mod f of x and b of x mod f of x are strictly less than that of f of x. So the sum of the polynomials will be a polynomial of degree lower than that of f of x. But that's not true for, say, the integers. So we'll make use of this property in just a. So earlier we defined this notion of irreducible polynomials, right? That is polynomials which cannot be factorized into smaller polynomials. So the only divisors are 1 and itself, or constants and scalars and itself. Now, what we want to prove is sort of the unique factorization theorem. So we know that any number, any integer, can be factorized as a product of prime numbers. So similarly, we can prove a unique factorization theorem which says that every polynomial can be uniquely factorized as a product of irreducible polynomials. And this is true irrespective of what the field is. So far, in all our discussions, we never really made an assumption on f, right? We didn't make an assumption that f is, say, finite or infinite. Or this in general holds true for all fields, but a polynomial ring over field. So it's uniquely factorized up to a scalar multiple. Scalars. So in particular, if we demand that the leading term of each of these irreducible polynomials is equal to 1, the leading coefficient, then it is some scalar times a product of unique product of irreducible polynomials. Correct. 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 I will. So basically, I'm going to try to construct finite fields, right, of arbitrary size. Right. So far, the only kinds of finite fields we have seen are prime fields, right? Set of integers modulo p for p a prime. So we know that we can't construct. I mean, if you look at, say, the set of integers modulo 8, this is not a field. Right? But suppose I want to construct a field whose size is equal to 8. Is it possible to do so? I'll show that it is indeed possible to do so, and we'll see how to construct the field. That is what I'm getting at using all of this. So in principle, over any finite field, how do you add, subtract, multiply, and divide? Right? That's what we want to. Okay. It is not a field. Yeah, using polynomials, I will construct a finite field whose size is 8, whose order is 8. In fact, this procedure will let you generate all possible finite fields. So this will give you the exact structure of every finite field. Not infinite fields, of course, but in principle, we'll see that it's possible to construct any field using a base field. You can construct a higher order field, even if it's infinite, and they can be described in a particular fashion using polynomials. So first, so unique factorization theorem. So given any f of x, I can uniquely factorize it into a product of irreducible polynomials. So suppose that f of x is equal to a1 of x, a2 of x, am of x. Okay, it's also equal to this times some scalar, okay, and a1, a2, am, all of them have the leading coefficient equal to 1. Similarly, I can also write it as b1 of x, b2 of x to bn of x times beta. Suppose these are two different ways of factorizing f of x. No. There's nothing. They're just different polynomials. The only point is that a1, a2 up to am are all irreducible. b1, b2, b3 and so on are irreducible. They could be in any order. They could have any degree. Doesn't matter. I'm making no assumptions. Okay. So now, obviously a1 divides f of x. So a1 should divide the product of these as a1 of x divides b1 of x, b2 of x to bn of x. Now, my claim is that since b1, b2 and so on are irreducible, a1 of x should be equal to one of these. It doesn't matter, it's a scalar multiple, right? So it's a scalar, so a1 of x should divide one of these, because a1 of x cannot divide beta. Divides bi of x for some. In fact, a1 of x should be equal to bi of x okay. All right. So then, okay, so there's one a1 and there's some a1 somewhere sitting over. Let me divide a1 on both sides. I get a new polynomial. I'll inductively proceed, right? So now I've removed out a1 from both sides. Then I have a2. So using exactly the same argument, a2 should divide the product of these divided by a1, and therefore a2 should divide some other bj for j not equal to I. So therefore I can again cancel those out and I can keep proceeding, right, until all I have is a scalar multiple, all I have is a scalar on the left hand side. But that must imply that on the right hand side also I have the same scalar. I can't have any. So it must mean that this is exactly the same. So over any field, a polynomial can always be uniquely factorized as a product of irreducible polynomials. So what does it say with the real field? So take any real polynomial we know that the only irreducible polynomials are polynomials of degree 1 and potentially polynomials of degree 2. So we can always write every real polynomial as a product of polynomials of degree 1 or degree 2. And those of degree 2 should have complex roots. That gives you the unique factorization theorem for the real field. What about the complex field? We know that every complex polynomial has complex roots, right? So what are the irreducible polynomials over C of x? Constants and how can you have a second degree polynomial? A polynomial with complex coefficient. Complex coefficient. So take any polynomial with complex coefficients. Will it always have a complex root? Okay. So of course constants are irreducible. What about x? What about polynomials of degree 1? By definition, they're always irreducible. The coefficients can be complex, right? So if it's a real polynomial, then it has to have conjugate. But in this case, every polynomial with complex coefficients has complex root. Like any polynomial always has complex. So of course, all degree 1 polynomials are always irreducible. Do there exist degree 2 irreducible polynomials over the complex numbers? May or will? So what does it mean for a polynomial to have a certain root? So if alpha is a root, if alpha is a root of some polynomial f of x, what can you say? Of course, you know that f of alpha is equal to 0. But what can you say about x minus alpha? X minus alpha will divide f of. So now if you look at C of x, that is the set of all polynomials with complex coefficients, can there be a degree 2 irreducible polynomial? There can't. The only irreducible polynomials are those of degree 1. But on the other hand, over the real field, you can have irreducible polynomials of degree 1 or degree 2. Correct? So if you look at the set of real numbers and the set of complex numbers, obviously the set of real numbers is a field. It's a subset, it's a subfield of the set of complex numbers. So if you have some f, which is a subset of f prime, a strict subset of f prime, where f and f prime are fields, then we basically say that f is a subfield of f prime, or f prime is an extension field of f. So the field of complex numbers is an extension field of the field of real numbers. So you can get a subfield by taking some subset of the field. Right? But how is it possible to systematically construct extension field? Right? That's something that we want to investigate. Which leads us to this very nice theorem. So basically you take any field, okay, and you look at the ring of polynomials over basically a set of all polynomials with coefficients from f, and take any irreducible polynomial. The claim is that the set f of x modulo the set of residues of f of x modulo this irreducible polynomial is a field. So this is just set of all a of x mod f of x Is the statement clear? So let's first try to prove this. I mean, the proof is fairly simple, given all that we have so far. And then we'll try to construct some fields. So what do you need to show? What do you need to do in order to show that this is a subfield? So if you look at a of x, f of x mod f of x, take all polynomials modulo f of x, does it form a group, additive group? Because you're adding everything modulo f. So no matter what f of x is, whether it's irreducible or not, this is always an abelian group. And once again, irrespective of what f is, multiplication will always be commutative, it will be associative, and distributivity will still hold. So those three properties are guaranteed no matter how you choose f. The only, and does a unit element always exist? Multiplicative identity. So you take the multiplicative identity from F, the base field, right? That is also a multiplicative identity for f of x mod small f. So take any a of x times 1 mod f of x. This is equal to a of x for any a of x in this particular. So let me give this a name. Let me call this f subscript f. Okay. So the only thing that we have to be careful about is whether inverses exist, because even when we were trying to look at the set of integers modulo p, we saw that if p is not prime, then some elements don't have inverses. We have to check whether inverse. So if inverses exist for all elements, then basically we know that this forms a field. That's the only tricky part over here. So let's try to do that. So what do we know about f of x? F of x is irreducible, right? So for any polynomial, right? So every polynomial in this set, remember, since this is the set of all polynomials modulo f of x, what can you say about the degree of a of x? It will be strictly less than the degree of small f of x. Okay, so what can you say about the GCD of a and f? Do you agree? F of x is irreducible, therefore it cannot be, it is not divisible by any polynomial which has smaller degree. So the GCD of a and f should be equal to 1. What does this imply? It implies that you can find some c of x, d of x, right? Some polynomials such that a of x times c of x plus f of x d of x equal to 1. So now let me take mod f of x on both sides. So what can I say about a of x, d of x plus f of x, d of x mod f of x is equal to 1, because right hand side mod f of x is equal to 1. 1 mod f is equal. But what about the left hand side? This is a of x, c of x mod f of x plus f of x, d of x mod f of x. What is the second term equal to? What is f of x times d of x mod f of x? What is the remainder when f of x and d of x 0? So f of x, d of x mod f of x is equal to 0. Correct? So a of x, c of x mod f of x equal to 1, which implies that c of x mod f of x is the inverse of a of x. So inverses exist, and therefore it forms a field. All right. So now that we established that it's possible to construct fields in this particular manner, let us try to go ahead and construct some fields. Let's start with the field of real numbers. Okay. Okay, take R. So this is my base field. Okay. Now give me one irreducible polynomial. No, not degree 1, degree 2. Let's take x square plus 1. Okay. So x square plus 1 is irreducible. Right. So what will R of x mod x square plus 1 look like? So this is some set of polynomials, correct? So this will be what degrees will the polynomials have? 1. So they're all degree 0 and 1 polynomials. So it is of the form a plus b times x for a and b in R, correct? How is addition defined over here? So it's addition mod x square plus 1. So if I take a1 plus b1x and add it with a2 plus b2x, what do I get? So this is mod f of x. The sum is going to be some polynomial of degree 1. So therefore, this mod is redundant. So this is exactly going to be equal to a1 plus a2 plus b1 plus b2 times x. Basically, the coefficients just get added up, nothing different. So multiplication is where things become interesting. So let us look at a1 plus b1x times a2 plus b2x mod x square plus 1. Okay. What is this times this equal to? A1 a2 plus a2 b1 plus a1 b2 times x plus b1 b2 x mod x, correct? But we know that this is equal to this mod x square plus 1 plus this mod x square. So this is equal to a1 a2 plus a2 b1 plus a1 b2 times x plus b1 b2 x square mod x square plus 1. Or this is effectively equal to b1 b2, since these are scalars, b1 b2 times x square mod x square. So what is the remainder when x square is divided by x square plus 1? Or in general, b1 b2 x square is divided by, yeah, b1 b2 square 1. So this is minus b1 b2. Or in other words, x square mod x square plus 1 is minus 1. So this is equal to a1 a2 minus b1 b2 plus a2 b1 plus a1 b2 times x. Right? Is this familiar? This is just complex multiplication. Multiplication of two complex. So you're doing exactly the same thing, but you're calling x as I, using a different notation for x. I, which is square root of minus. And the reason why you get square root of minus 1 is because you know that you're taking this mod x square plus 1. So x square mod x square plus 1 is minus 1. So which is basically the same as saying that calling x as square root of minus. Alright, so this is one way of constructing the complex numbers from the set of real numbers. Okay, now let's look at another example. So we had f2. So let's take our base field f2. We know that the set of integers modulo 4 is not a field. And that is because inverses didn't exist. So let's maybe just write that down. Let's look at, this is Z4. So the elements are 0, 1, 2, 3, and my multiplication is modulo 4. Let's just write down the multiplication table for 0, 0, 0, 0, 0. 1 times 1 is 1, 2, 3, 2. 2 times 2 is 4, but 4 mod 4 is 0. 2 times 3 is 6. 2, 2, 3 times 3 is 9. This is 1. So in this case, 2 does not have an inverse. Correct? Okay. But I still, let's say that I want to construct a field of size 4. Finite field of size 4. So let's take an irreducible polynomial over f2. We've seen that x square plus x plus 1 is irreducible. Right? Now let us look at f2 of x mod x square plus x plus 1. Right? So this will be some set of polynomials of what degree? Degree 1. So it's basically the following set. 0, 1, x, and 1 plus x. Addition is just term-wise addition, so there's nothing interesting going on over there. But let us now see multiplication. Obviously, this first row is all zeros. Right? The second row is same. It's x. What is x times x? X square. What is x square mod x square plus x plus 1? Which is x plus 1 or 1 plus x. Okay, what is x times 1 plus x? So this is 1. Similarly, this is 1. What is 1 plus x times 1 plus x? Yeah, so 1 plus x, the whole square is going to be 1 plus x square. This mod x square plus x plus 1 is going to be x. Let's look at this multiplication table now. So this has, it's exactly a permutation of the elements 1 x and 1 plus x, right? So every element has an inverse, right? Because every row has a 1 and every column has a 1. It is symmetric, so commutativity is preserved. We didn't really have to worry about that anyhow. So inverses exist. That was the only property which was not satisfied in general by say, polynomials modulo something. So this is a field. So in general, as long as you can find an irreducible polynomial, you can always construct a field extension. And now you know exactly how to do arithmetic over these finite fields. So if I want to take two elements of this finite field, addition is just term-wise addition, which is straightforward. But if I want to do multiplication, so multiplication of two elements in the finite field is basically the same as performing multiplication modulo some polynomial. So it's basically polynomial multiplication and then find the remainder when divided by some other polynomial. So remember, this is a field, but you are performing polynomial additions and polynomial multiplication remainders. So field operations essentially correspond to polynomial operations. So here's a fact. Of course, I'm not going to prove it. So for any prime number p and positive integer n, there exists an irreducible polynomial. There could be multiple. Of degree n in Fp of x. So what this implies is that you can always construct a finite field. Okay, so just before that, in this case, what is the size of the finite field? Suppose I take an irreducible polynomial of degree n, okay, and look at Fp of x mod that particular polynomial. How many elements will be there in that set? Take Fp of x mod, say, a of x for some polynomial a of x of degree n. How many elements are going to be there in this particular set? Why? Why? Correct. So it's a0 plus n minus 1. So this has size p to the power n. So what this claim implies is that for every prime p and integer n, it is possible to construct a finite field of size p to the power n. Now, it turns out that these are the only possible finite fields. So basically, it is not possible to construct a finite field of any other size. So if f is a finite field, then the size of f is equal to p to the power n for some prime p and some positive integer. So for example, it's not possible to construct a finite field of size 10 because 10 is not a power of a prime. It's a statement. I have not proved anything yet. I'm not going to prove it. Of course you can, but it turns out that that's a fact. Yeah. So basically, you take an irreducible polynomial of that particular degree, of degree n, and then look at fp of x mod a of x. That is going to be the finite field. Yeah, a finite field of size p to the power n. Now, it turns out, that again requires a separate proof, that irrespective of which, so there could be multiple irreducible polynomials. But no matter which irreducible polynomial you take, the fields turn out to be isomorphic to each other. Basically, there's a one-to-one map such that addition and multiplication is there's also a one-to-one correspondence. It's basically a relabeling of one of those sets gives the other set. Yeah. Yeah, there could be multiple irreducible polynomials of the same degree. Yes. So you take any two fields of size p to the power n, they're isomorphic to each other. Correct. So exactly. So that matters. But there are also other structures that I mean, so all finite fields have a certain multiplicative structure as well. So it turns out that you take any finite field and you look at the set of all non-zero elements, then this will form a multiplicative cyclic group. What do I mean by a cyclic group? There exists some element such that every non-zero element can be expressed as that element raised to the I for some integer. So if you want to really multiply two elements, so one way is of course to do this polynomial multiplication and then find the remainder and so on. But then if you identify this so-called primitive element which generates all elements, then multiplication becomes much easier. It just basically you just multiply. It's just like adding the exponent. That greatly simplifies. So again, there are a lot of things you can do. This rich algebraic structure, which unfortunately we can't get into in detail. But certainly any book on coding theory will have all of these details. So even the book by Ron Roth, for example, that has a lot of details about how do you construct finite fields, the multiplicative structure, and so on. Many results that I have not discussed so far in this particular course. But for now, At least for our purposes, all we need to know is it is possible to construct finite fields of these orders, and we know how to perform arithmetic within these fields. So one way is sort of the brute force way, you just everything is using polynomials. And let's assume that we can doing that is fine. Although polynomial multiplication and whatever remainders is not always very easy to do. Okay. Any questions? Some of them could be irreducible, some of them could be reducible. They're elements, right? So there are some elements of, so certainly all polynomials of degree 1 are going to be irreducible. So this is going to be the set of all polynomials of degree n minus 1. So that is this field. Correct? Yes. Correct. Yes. Correct. So then it will be, so it's basically going to be all polynomials of degree 3 up to degree 3. Right? So it's going to be 0, 1, x, 1 plus x, and then x square, 1 plus x square, 1 plus x square, and then x plus x square, eight, exactly 8. So this is going to be the set of elements. This is of course one representation of this field, and then addition and multiplication is modulo, again it's going to be modulo some irreducible polynomial. So you have to choose an irreducible polynomial of degree 3, otherwise you don't get a field. Correct. Yes. No matter which polynomial you use, effectively you are getting the same field, but it's going to look different. But the algebraic structure is exactly the same. Yes. Correct. And but we are getting same elements. They're not exactly the same. That is because they are the same. So this is x mod that polynomial. Any questions? Correct. Correct. This is 4 elements, right? 0, 1, x, and 1 plus x. 4 elements. Yeah, so this is generally called f2 square or f4. It's exactly this. So that is why I can confidently say it's f4, and similarly f8, even though there are two different irreducible polynomials of degree 3, they essentially give the same field. So if I say F8, then there's exactly one field which corresponds. No, not exactly. They're not linear. Exactly. Yes. Which one? So here again, yeah. So you mean to say if I take different irreducible polynomials, yeah, if I take different irreducible polynomials, they'll all be a1 plus a2 x. Suppose there were two irreducible polynomials of degree 2. So then all of them would still be of the form a1 plus a2x, right? But really the way you should think about this is basically you have these equivalence classes. Right? So if you take f2, so f2 of x is an infinite set, correct? It's an infinite set. Now what are you doing? You're taking modulo this some polynomial. Right? So basically what you're doing is you're splitting f2 of x into various equivalence classes, exactly 4 equivalence classes. The set of all polynomials whose remainder is 0, set of all polynomials whose remainder is 1, those with remainder x and those with remainder 1 plus x. Now if you choose different polynomials, so different irreducible polynomials, then the equivalence classes are going to be different. Correct? Yes. They are different. So they're actually different sets. Right? The remainders are same. So these are essentially, you can think of them as, yeah, these are the like the coset representatives. When you take the remainder, these are precisely the coset representatives. So in both cases, the groups are different. If you look at f of x times x square plus x plus 1, that is a group. Right? It's a subgroup of f2 of x. The coset representatives, it has exactly 4 cosets, and these are going to be coset representatives. Now if you take a different polynomial, again you'll get the same coset representatives, but the cosets are different. They're different sets. Yes, so there is a mapping between those cosets such that you still get the same multiplicative and additive structure. So that is what it means by an isomorphism, right? So if I take, so okay, so what exactly is an isomorphism? So you take any f and prime, we say that f and f prime are isomorphic if you can find some bijection, let's call it phi from f to f prime, such that phi of a plus b is equal to phi of a plus phi of b for all a b in f, and phi of a b is equal to phi of a times phi of b a b in f. So just a bijection is not sufficient. It has to satisfy these two properties. So for example, let us take these two cases. So yeah, these two. So these two are different sets, right? Z4 and here. But now it is impossible for me to construct a bijection from Z4 to this. Sorry, it's possible to construct a bijection, but there is no isomorphism, right? Because if you look at this, if you say that 2 is mapped to some other element, some non-zero element, so the 0 obviously has to be mapped to 0. So if 2 has to be mapped to any one of these elements, that's not possible, because 2 multiplied by 2 should give me 0. Whereas if I take any other element and multiply by itself, I cannot get to 0. So there is no isomorphism from Z4 to F4, but there is a bijection from Z4 to F4. Any mapping will do, any one-to-one mapping. So in that sense, yeah, all fields of the same size are essentially identical. They're isomorphic. But then sometimes some irreducible polynomials may be more convenient in terms of maybe their implementation and so on. Certain representations of the finite field may be more helpful than others for certain applications. Any other question? So, because the basics are all covered in the textbook by Ron Roth, the textbook that we are following. But there's an entire book on, if you want to know just about finite fields, there's a huge book on only finite fields, constructions of finite fields. I don't remember the exact title, but one of the authors is, yeah, I'll maybe post it in on Google, because I don't, the name is a bit complicated. The name of the author itself is a bit complicated. That's considered to be the Bible for finite fields. But generally, most classical textbooks on coding theory will have a good treatment of finite fields. So let's stop here.